Okay, so what is done is you have a frame, let's say you take out a particular portal from a right. So if I have to use this particular member, this particular beams at this particular level, I would use the substitute frame as right, and the loading on this particular beam being defined by the tributary area, load coming from the tributary area of the slab uh, on that floor, and you can see this is the tributary area that you may have, and it can be rectangle, triangle, trapezoid, some kind of thing. So these are the tributary area, and this will lead to total loads right. So in some resources you will find that these columns have to be taken as the full height and then anchored, ensuring or assuming fixity, total fixity at the far end. Or alternately, you may also find some resources talking about half of the length of this column and assuming hinge conditions at this point at the mid height. That you will find that the moment in the columns usually is of the order of usually has this variation, uh, the reversible signs, and the mid span is usually the point of contraflexure, and that is why you can assume hinge at the mid span, mid height of the columns. So now this becomes, as compared to analyzing the complete frame as a at one go, it is a much easier and manageable task, just concentrating on the analysis of this simple substitute frame. The moment distribution is very simple, and it converges very quickly, and you get the frame member forces very easily, very quickly, right? And of course, it agrees with the classical theory of Saint Venant's principle that the effects are localized. So whatever is happening in this at this floor, the effects of those loads will have progressively less effect on the floors above and floors below. So and that is why it is permissible to use this substitute frame. The only issue is, what is the critical condition? If all the spans are loaded, and obviously this is continuously cast, so it is a continuous monolithic construction. So then there are going to be issues here with respect to the loading pattern. How this loading pattern, if these alternate spans are loaded, then there will be other, some kind of bending moment distribution. If all the spans are loaded, then there will be another sort of bending moment distribution, and so on, right? For example, in this particular form, the deflected shape might as well be something of this kind, and that might be also similar to the bending moment. Bending moment might be somewhat like this. Right? But if the alternate spans are loaded, then it will change the bending moment distribution, isn't it? Because in that case, if the alternate spans are loaded, let us just look at the condition when alternate spans are loaded. So let's say we consider loading on this span and on this span. So obviously this is going to have deflection on this type. Right? And this will have an entirely different bending moment distribution, because these two joints will obviously try to rotate and have a hogging moment, kind of deformation in this unloaded span, and similarly this unloaded span will also have hogging moment. And this has a critical combination on the loads that are coming onto the structure. So typically alternate spans are loaded, and all other different alternate spans loading are considered to determine the critical load condition. So this is normally used, alternate span loading is normally used for gravity load, and very convenient for quickly estimating the design forces and actions on the beams and columns. But this kind of alternate span loading is not to be used for earthquake purposes. Now we come to this is how substitute frame method, that is how you normally use for gravity load. If you have to do a hand calculation, then substitute frame is a very convenient tool for quickly estimating the forces and working out the design forces. Right, so I'll read out the loading pattern considerations. The arrangement of imposed loads, you will find design dead load on all span with full design imposed loads on two adjacent spans, and design dead load on all spans and with full design imposed load on alternate spans. So these are the two conditions, and so dead load is of course there on all the spans, but imposed load is considered on alternate spans or two adjacent spans, and whichever is the critical combination, that is what is used to develop, compute the design forces. So this is how. Loading pattern, as I said, full dead load on all spans and full imposed load on alternate spans, and second one is full imposed load on adjacent spans. So these two conditions, you evaluate the dead load forces and then we set it aside, and then we would of course take the seismic analysis, and seismic analysis of course has to be on the complete structure, or even the alternate frame method. But typically for lateral load analysis, we use the complete frame because simple assumption like rigid floor diaphragm will allow you to reduce the degrees of freedom considerably, and it is easy to find story shears at each floor and then distribute it to individual bays, and equivalent lateral load analysis can be then carried out to find out the earthquake effects. So I guess this matter has been covered by Digvijay, the lateral load analysis.
Yes, sir.
So how do we estimate these lateral load from the design spectrum, considering the dynamic properties, natural period and mode shapes, and how do we arrive at these lateral forces? So once you have the lateral forces coming onto the structure, then obviously you can work out the member forces, and then add them in the using the load combination, different load combination, and of course when earthquake load is applied, then the dead plus imposed load weightage is reduced for that particular member forces. Now one thing that you need to understand, although we use sequential analysis, right, that is, first use dead load plus imposed load. Static analysis, and then you make use earthquake or wind loads, right? So earthquake or wind loads would also be acting in the similar fashion, although the mechanics of deriving the nature, the quantum of these forces is different from what how we do it in case of earthquake load, but effectively on the for the structural analysis consideration, the representation is more is similar. Both of them are considered as a lateral load on the structural system. So use earthquake wind loads subsequently, and this is dynamic analysis. Ideally it should be dynamic analysis, but you can use it using either response spectrum method or even equivalent static analysis. So equivalent static analysis is when you would derive these lateral forces distribution over the height and then consider these forces acting as static forces, and of course these are always added plus or minus to take care of the reversible nature of the sign and consider the worst possible condition. So you would have the load effects as gamma dead load multiplied by dead load plus gamma imposed load multiplied by the imposed loads. So typically these partial factors for dead load and imposed loads are identical, plus or minus gamma earthquake load and multiplied by whatever is the effect of seismic loading, and that is how you will find the demand. Right, these are the member forces for which you need to provide adequate capacities. So rather than member forces, I would rather say the demand. So this is the demand, and for which you need to build adequate capacities. Have to be provisioned. Right, and once you have provided adequate capacity in the system, your design has been achieved. Right. So now all set. This is what you do in case of design. So once you do the analysis, you compute the member forces, you add because of earthquake loading or wind loading, you add the member forces, add or subtract member forces to the member forces that are computed using the static analysis for dead load and imposed load. And you can carry out the dead load imposed load analysis using a substitute frame method very quickly, and that should give you the numbers to work with for designing the sections. Then you work on with the particular section detailing, and you have the design, and finally you check up the drifts. After the design, preliminary design, you again go back and calculate the complete displacements and deformations and check the drift limitations. If the serviceability conditions are violated, then again you go back to the respective members affecting that particular parameter and revise the design suitably. So pretty simple, isn't it? Now let me throw a little dampener on this simple picture. First thing is the basis of earthquake resistant design is inelastic deformation in the event of strong earthquakes. So this is the key phrase, inelastic deformation. So if the system is inelastic, then for inelastic system, is it justified? What I am trying to say here is what we have done, what we suggested, that we compute this analysis, sequential analysis. We estimate the member forces for dead load and imposed load, set it aside, and that is designated as this D and I, or I can just I assume these partial factors to be identical for dead load and imposed load. So it's just dead load plus imposed load, right? So that I set it aside, and then on to these member forces that I compute, I add the additional forces, additional demand that is coming from earthquake or wind load, right? So let's only talk about earthquake load. So I add these earthquake effects on top of these member forces that have been computed earlier. So this is what it is. So the forces computed using dead load. So I would say these are the member forces due to dead load, dead and imposed loads. And this is member forces due to earthquake loads, right? So computing these member forces due to dead and imposed loads, setting it aside, and then adding to those the earthquake load effects that you have computed, as shown by Digvijay in the class, that you do using response spectrum method and otherwise equivalent static procedure, and then add up. So how justified it is? Obviously, it is a nonlinear system, so this superposition as implied by this summation is obviously invalid. So for nonlinear systems, superposition is invalid. So obviously this cannot be true. So this is not equal. So what to do? But you still do this, isn't it? All your softwares that you have been using, they do like this: analysis for gravity load, imposed load, and then using appropriate, you just combine them using appropriate load factors and combine them with the analysis of earthquake loads, isn't it? Any experience you have with any software system? Are you aware of anything? Any analysis using computer platform? STAD or SAP or anything? ETABS?
Sir, Stat Pro heard about it and little bit know about it.
Okay, so you have not used any uh, software as such for analysis. Okay, fine, doesn't matter. So, even the code allows you to add these forces. So, obviously, the code software systems will do that. But what is to be noted here is the difference under what conditions. You need to understand that actual behavior does not depend or does not give any weightage to your assumptions in the analysis. It is the other way around. The assumptions that you make in analysis to simplify your life, they have to be consistent with the behavior that is expected during large earthquake, strong earthquake, because minor earthquakes, obviously nothing is going to happen, so you don't really bother about minor earthquakes. But it is in the strong earthquakes, case of strong earthquakes, what is going to happen, that is what should be in area of concern, and your analysis should be reflecting that situation. So first thing that you need to consider is seismic analysis should take cognizance of non-linearities. So first source of non-linearities is the uh, very simple stress strain curve, right? Even your stress strain curve of the concrete is non-linear. It's not a straight line. Even for the elastic range, when you do not expect any cracking or any significant uh, permanent deformation, permanent effect, right? So even the stress strain curve of the concrete, confined or unconfined, is non-linear. Something like this, right? So if this is non-linear, then so if the stress strain curve of concrete is non-linear, what are the implications? One implication is, of course, uh, what is the elastic modulus? What is the elastic modulus? By definition, it should be the tangent to this curve. Now, obviously, this tangent is changing at every point at different strain levels, right? So, it is variable with respect to the strain. Right, so that's the actual elastic modulus that you have. Uh, it will be somewhere here, it will be somewhere here, it will be somewhere here, it will be somewhere here. And that has effect on stiffness changes with epsilon. So I would rather say effective stiffness changes with epsilon. Right, and what are the sources? I mean, the effectiveness stiffness depends on stiffness of an axial member is EA by L, right? So elastic modulus multiplied by area of cross section divided by the length. So that's the stiffness of the truss element that you have. And what is the stiffness of a flexural element? Is EI by L cube, something similar, proportional to EI by L cube. In case of shear beam or shear building, the story stiffness is proportional to 12 EI by L cube, right? So Young's modulus, modulus of elasticity and then the moment of inertia, area moment of inertia, and of course the uh, length. What is the length? So larger the length, more flexible is the system, and larger the moment of inertia, more stiff is the system. So that's why you get higher rigidity with increasing the depth, because moment of inertia is I bd cube by 12. Right, so effect of depth is much more stronger than increasing the width of the beam. So the stiffness of the beam, flexural capacity, flexural rigidity of the beam would increase much more rapidly if the depth is increased rather than the width, right? And that is why you have so much uh, reservations about the concept of flat slab, wherein the beam is practically merged in with the slab. So the depth is only of the order of 110 or 150 mm, and same as the that of the slab. So practically you do not see anything, any beam, and that obviously has a very reduced stiffness, because the depth is very low. You may increase whatever width you may have. Of course, there are limitations to having the uh, width of the flange as a L beam or T beam, as the situation may arise, as may be the situation, but the stiffness is not really much if the depth is very low. Now the question here is, what are these B and D? So now I have something that is peculiar to earthquake situation. If I have this cross section of the beam, let's only consider the rectangular beam at the moment, right? So then I define gross moment of inertia as BD cube by 12, and compare this with this is, I would say, AC, core concrete. Confined core concrete. Because you see, when the earthquake, strong earthquake happens, then all this area that you see here unconfined concrete will be severely cracked during strong earthquakes. So this material is as if it is not there. It's not participating in action at all. It's a completely cracked section and offers no resistance whatsoever, and it is only the confined core that is inside the lateral ties, the concrete core which is bounded by the lateral ties, that can withstand large amount of strain, and that will be able to participate in structural action. So what is done is this stiffness, this uh, you need to, when you, obviously the analysis, the member forces would be governed by the stiffness of the members that we consider in analysis, right? Now the stiffness in case of earthquake loading is going to be much smaller than the stiffness that the structure would have during normal dead load conditions, right? And therefore the seismic analysis would be based on reduced properties, and uh, and therefore you will also find that the partial factors of load combination, they are reduced whenever the earthquake load is considered. That is to, in a way, to take account of the flexibility, increased flexibility in the case of earthquake load, reduced stiffness. So if the stiffness is low, then obviously the forces are also proportionately decreased. So what is the extent of this reduction? Obviously, if you consider the area of concrete, this column, your axial stiffness is EA by L. Now confined core will, of course, this also depends on the kind of axial force. If it is tensile force, then obviously you would not be worried too much. But if the force in the column, dead load force, static force in the column is of compression, then obviously the stiffness would be much reduced and it will be much more vulnerable. So typically what is done is core moment of inertia is considered to be of the order of 0.4 times gross moment of inertia. So the seismic analysis is performed using this simplified assumption. The concrete core, moment of inertia of the concrete core is approximately 40 to 50%, less than 50% of the gross moment of inertia of the outer dimensions of the members. And these simplification, because now it becomes very simple to implement in a computer program. You already have the dimensions, you already have all the gross section properties provided. Then it's only a matter of using a scaled down section properties to derive the stiffness, revised stiffness of the members and work out the design forces. And obviously your time period is to be estimated using this cracked section properties, and the lateral forces that you use for this lateral load analysis, they will be, of course, they will also be estimated using these cracked section properties. So I shall stop here now, and in our next lecture we will look at the design issues. for the ductile frame. Any questions?